Hey guys, this is Mrs. Hardin, and this is Advanced Math 3.1. We are going to be working on roots and radicals, and today we are expressing roots. You are going to need a calculator for this unit, probably one a little bit better than the red calculators that I provide for you in class, so make sure you bring your own calculator. Our biblical application for this unit is this: God blesses His people with the abilities and skills to succeed in their life work to His glory. You guys have skills and abilities in math, and you have been given the opportunity to use those abilities to do some kind of work in life, whatever your career or whatever path you choose, and to bring glory to God with those abilities. So let's take a quick review of perfect squares. Think about perfect squares. We've got two numbers. 1 times 1 equals 1. We've got 2 times 2 equals 4. We know perfect squares are when we take a number times itself. So if you think about the shape of a square, we know square is equal on all 4 sides. And if we were to find the area of that square, we would take 1 times 1. And that gives us 1. Okay, if you look at a 2 by 2 square, we've got 2 units on one side and 2 units on the other side. 2 by 2 is 4. Our other perfect squares, we've got 3 by 3, 4 by 4, 5 by 5, 6 by 6, so forth and so on. So any number times itself makes what's called a perfect square. Going back to geometry and reviewing that idea that a square is the number of units, same number of units on each side. So here's a 3 by 3 square. I'm not going to draw all of these, but you guys get the idea. And a perfect cube, if you think about what you know about a cube here. Sorry, this is going to be a very rough drawn cube here, but a cube is the same length on 3 sides. So this is a 1 by 1 by 1 cube. 1 by 1 by 1 equals 1. If we were to make this 2 by 2 by 2, let's try a picture of a 2 by 2 by 2 cube here. You can see that a perfect cube, in this case, 2 by 2 by 2, would be 8. And if we were to somehow be able to take this cube apart, you would see that there are 8 smaller cubes making up this 2 by 2 by 2 cube. Our other perfect cubes include 3 by 3 by 3. So 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, so forth and so on. You can see the first 10 perfect squares and perfect cubes up on the wall in the classroom. So when we're talking about squares and cubes, a lot of times what we're given first is the length of each side. Like here, we're told the length of each side is 2, and we need to find the total area or volume, if you will, that cubed result. Well, when we're dealing with roots, we're actually finding our way backwards. So in this example, when we want to find the square root of 16, imagine that you have a square made up of 16 tiles, or 16 units. It would look something like this, although better drawn than mine. So if you count, there are 16 little squares in here. You can count it if you don't believe me. And we want to know what number, how long each of those sides are. Basically, what is the root of our square? If you count that bottom row there, you will see that there are 4 units at the root of that square. Each of our side is 4 units long. So in a square of 16, what is the root, that's that symbol there, the root of our square? Well, we know that it's 4. What about 361? What is the square root of 361? 19. Nice job. You can use that, type that into your calculator. Most of you will type the number first and then hit the square root button. If you're dealing with a graphing calculator, you're going to hit the square root button first and then the 361. Now this is wanting to know the cubed root. So we have a cube with a volume of 64. What would be the length of each side? The cubed root of 64 is 4. Again, you can type that into your calculator. You might have a button that has the cube symbol, or you might have a button that looks like this, or a button that looks like this. that allows you to do the different roots other than just the square root. Our lesson objective for today is that you, the student, will estimate and simplify radical values. Squaring a number and taking the square root of the result are inverse operations. Like addition and subtraction are inverse, and multiplication and division are inverse. So taking 4 squared is 16, and then if we want to undo that, to the inverse operation, we would take the square root of 16, which would bring us back to 4. So if we ever want to undo a square number, we take the square root. Those are inverse operations. The square roots of 9 are 3 and negative 3. The square roots of 16 are 4 and negative 4. We know that because negative 4 squared equals 16, just the same as positive 4 squared equals 16. So when we take the square root of 16, for example, our answer is not just 4, but is actually positive or minus 4, plus or minus 4. Either one of those numbers would work. A square root is one of a number's 2 equal factors. The radical sign is the symbol for the square root. This is the radical symbol, and that is the symbol that we need to find the square root. The radicand is the expression under the radical sign. So let's go back and review this then. In this particular instance, we need to find the square root of 16. And this is my radicand. That's the expression under the radical sign. If we want to find a different root other than the square root, we would put a number outside called the index. So this would mean find the cubed root. We could also find the 4th root, 5th root, 6th root of different numbers. The square root of 9 has 2 values. We already talked about this. Every square root has a positive and negative value, so plus or minus 3. To avoid any confusion, we use the radical sign to indicate the principal root. Basically, we want to know the positive square root. If the negative square root is desired, a negative sign is placed in front of the radical sign. So this is our principal root, or a positive square root. And if we want the negative, then we put a negative in front of the radical sign. I want the negative square root of 9, so negative 3. Let's do a few examples together. Pause the video, try them on your own, and play when you are ready to check your work. Positive square root of 4 is 2. The negative square root of 16 is negative 4. Now what about the square root of 7? It's not a perfect square. And so if we were to put that into our calculator, we get 2.6457. Not a nice, neat number. When a square root doesn't make a clean break, just keep it as root 7 instead of multiplying or trying to find the decimal. Now sometimes you can simplify a square root. 63 is not a perfect square. But I know that 63 is made up of the factors 9 times 7. And I can write that as the square root of 9 times the square root of 7. And I know that the square root of 9 is a perfect square. So I can go ahead and simplify that as 3 times the square root of 7. Or, because there's this radical symbol there, I can just take out that multiplication symbol altogether and have 3 times the square root of 7. When trying to simplify a root, we need to know what the factors are and recognize whether any of those factors themselves are perfect squares. Let's try to simplify 300. Try it on your own. Play the video when you're ready to check your work. 300 is 100 times 3. I can write that as the square root of 100 times the square root of 3. I know the square root of 100 is 10, and the square root of 3, not a perfect square. I can remove that multiplication sign here and just have 10 times the square root of 3. In this case, this radical sign kind of acts like a grouping symbol, like parentheses or other grouping symbol where we know when they're right next to each other it means to multiply. An index is added to the radical sign to indicate roots other than the square root. So that small little number on the outside is if we want to find a root other than the square root. We can put a 3 there for the cubed root, 4 for the 4th root, and so on. A cubed root is one of a number's 3 equal factors. So it's a number that I can multiply by itself 3 times. Like we've already talked about in that picture of a cube, with the number 64, for example, the cubed root was 4. An nth root, n, is one of a number's n equal factors. So if we were looking for the 5th root, we would be looking for a number's factors that we've multiplied 5 times to get that number. We can replace that n with any number, 4, 7, 9, whatever. We've talked about how exponents and roots are inverses of each other. They undo each other. So if 2 cubed is 8, then the cubed root of 8 is 2. They just undo each other. See if you can find these cubed roots. Pause, check your work. Cubed root of 125. Well, we know 125 is 5 times itself 3 times, and the cubed root of 5 cubed is just 5. These undo each other. The cubed root and the third exponent undo each other, leaving us with just 5. The 4th root of 81. Well, I know 81 is 3 times itself 4 times. The 4th root of 81 is just 3. If you're not sure that the 4th root of 81, or that 81 is 3 times itself 4 times, you can do prime factorization. You know that 81 is 9 times 9, and 9 is 3 times 3. That was not a very pretty 3. So we know that 81 is 3 times itself 4 times. So if you're not sure of a number's factors, go ahead and do prime factorization to help you realize what those factors are. All right, try these on your own. Check your work after you've had a chance to work these out. Okay, 8 is just 2 times 2 times 2. And the cubed root of 2 cubed. The cubed root and the third exponent cancel, so we're left with 2. Cubed root of 1, well, 1 is just 1 times 1 times 1. Again, the cubed root of 1 cubed. The cubes cancel each other, and we've got 1. And the cubed root of negative 64. Negative 64 is just negative 4 times itself 3 times. Again, the cubed root and the cubed exponent cancel each other out, leaving us with negative 4. Now, we're talking about positive and negative numbers. The even root of a negative number is not a real number. So I could never take the square root of negative 16 because nothing times itself twice is a negative number. Negative 4 times itself twice is always positive. So the even root of a negative number is not a real number, since any number to an even power is always positive. But the odd root of a negative number is a real number. We saw that with the cubed root of negative 64. Because I can take negative 4 times itself 3 times and end up with a negative number. So odd roots of negative numbers are real. Even roots of negative numbers are not real numbers. So negative 4, not a real number, square root of negative 4. But the cubed root of negative 27 over 125, that's negative 3/5 cubed, which leaves us with negative 3/5. That's a real number. What about the 5th root of negative 32? If you said negative 2 to the 5th power, which is negative 2, you are correct. While some radicals are rational numbers, meaning we can write them as a fraction, like 4 over 2, for example, many radicals are irrational numbers. It cannot be expressed as a fraction, as a ratio of 2 integers. Irrational numbers are non-repeating, non-terminating decimals. They keep going and going and going. Irrational numbers can be either stated exactly as radicals, so we can just leave it in radical form, or we can round to a designated